So today we're talking about Taylor series, specifically the derivation of the Taylor series. I don't have any notes with me, so I'm hoping that this will go smoothly. Um, I consider the Taylor series to be probably one of the most amazing things in math, and it's like uh, it looks complicated at first, but it's actually the idea is pretty simple. And that is, if we have some sort of complicated function, like some sort of function we want to find the value of that isn't easy to find the value of by hand. That's the original motivation of the Taylor series. Like, say we wanted to find the sine of 0.1 by hand. So as you might know, it'll be kind of hard to do that. But people back in the days used to look at tables and stuff to figure this stuff out. But and it's funny because the original motivation for the Taylor series is to be able to calculate these types of functions like this by hand. But these things, Taylor series, they are incredibly important in physics and like anything. Lots of things you can approximate by the first few terms of the Taylor series. You'll get complicated differential equations that you can simplify vastly if you approximate them with Taylor series. You can rewrite functions in Taylor series. These things are just incredibly useful, and they never go away. And oftentimes, a lot of people hate them because they're not the easiest thing in the world, and they want to just be done with it and shoo them off and hope to never hear from them again. But they don't go away. They're just so important. And basically, the idea behind the Taylor series is, and I'm going to show a couple of pictures here I got from Wikipedia. We have, let's say, we have this function right here, the sine function, this blue one. And the idea is to find some sort of polynomial f of x that is equal to or very, very close to the sine function in a small domain, as you can see here, between like negative pi and pi. They're pretty much equal, and therefore we're trying to find a polynomial. Polynomials are easy to calculate by hand. So if we find this polynomial, it'll be easy to calculate sine, because all you do is just plug in the values in a polynomial, which you can do easily. So so what does that mean? How are we going to do that? Well, our polynomial, we're going to write p of x is equal to a0 plus a1x plus a2x squared plus a3x to the excuse me, sorry, x to the third plus dot dot dot. And it's just some infinite polynomial. We don't know how many terms it's going to be. And this is going to be equal to a function f of x. Now, in a certain domain. Now, what you do is you pick a value to quote unquote center the Taylor series at. Like, for instance, in this, the center is at 0, and as you get further from 0, it gets less accurate. You see, way out here, it's not accurate at all. So you pick a point to get close to, and you sort of equate the polynomial and the function at that one point, and then around the point, they're really close, if not almost equal, or equal enough to get good enough values. So now, if you pick that point to be 0, it's called the Maclaurin series, and if you pick it to be anything else, it's the Taylor series. So for the sake of ease and I don't know. Yeah, I'm just gonna say ease. We're gonna pick the center at 0, but you'll see at the end that it really doesn't matter where we pick it. So we're gonna center this at 0. So that means that f of 0, from our logic before, f of 0 equals the polynomial evaluated at 0. So what does that mean? That means f of 0 equals, now you plug in 0 into this polynomial, this infinite polynomial. Well, there's an x in every term except for the first term. So the only thing that's going to survive is the first term, a0 or a0. So now, our next leap of logic is, if these functions behave the same around a certain point, then it makes sense to say that their derivatives also behave the same way. Because if we go back to this picture, the slope of the tangent line at 0 is the same for both the pink and the blue line. So that means f prime of 0 is equal to p prime of 0. But what's p prime? P prime is a1 plus 2a2 plus 3a3 plus 2a2x plus 3a3x squared plus dot dot dot. It goes on forever. We see how we just took the derivative of this. So now we just plug in 0, and what do we get? We get a1. So now if the functions behave the same around that point, and that means their first derivative is the same, that also means that their second derivative is the same. So f double prime of 0 equals p double prime of 0, which equals, you take the derivative of this now to get p double prime. So it's going to be 2a2 plus 3a plus 6a3x plus dot dot dot. Now when you evaluate that at 0, you get 2a2. And if you were to do this again, you would say f triple prime of 0 equals p triple prime of 0 by the same exact logic, and you evaluate at 0, you get 6a3. And then you keep doing it, you would get 24a4. Let me just write the whole thing out so it's more explicit. P4 prime 24a4. Then if you do it again, if you write an easier way to write the primes is to write 5 in parentheses. That's not to the 5th power. That's, if it's in parentheses, that means the 5th derivative. So now equals p to the 5th derivative of, or not to the, p, the 5th derivative of p at 0, and this will equal 120a5. I believe it's 120. Yes. And you could do this forever, but what you'll notice is, well, here, this is enough data, I guess, to come up with our formula. If we look at this polynomial up here, we can actually rewrite this in a closed form, which would be k is equal to 1 to infinity of a sub n x to the n, or not n, k. Well, let me just change this to n because I usually use n. So this is just a summation, when n this actually starts at 0. This is a power series. When n is 0, you get a naught, and that's it. Then when n is 1, you get a1x, then a2x squared, and so on. So if we solve for all the coefficients, well, over here we have a naught equals, well, let's just let's write it down here. So we have a naught equals f0, And then we look at this one, a1 equals f prime 0. a1 equals f prime of 0. Then we look at this one, a2 is equal to, if you solve for a2 in this, a2 is equal to 1/2 f double prime of 0. And then you solve for this, you get, in this equation right here, you get a3 equals 1/6 f triple prime of 0. Then you get, I'm just going to write all of them then, why not, for completeness. A4, all these are done by just taking each one of these and solving for A3, A4, A5, etc. A4 is equal to 1/24 f fourth derivative of f at 0, and A5 is equal to 1/120 f fifth derivative at 0. Now, if we look at the coefficients of the, this pattern, 2, 6, 24, 120, is a well-known pattern. It's called n factorial. And it basically means, and the simplest way to show this is if you have 4 factorial, it just equals 4 times 3 times 2 times 1. So you basically just start from this number and just multiply down until you get to 1. And it turns out 4 factorial is equal to 24. Because you have 6 times 4, 24. And it turns out that the sequence n factorial, sorry, I didn't, kind of slurred my R there, goes as, it starts at 0. 0 factorial is 1. And that's not obvious at all. You actually can prove that with something called the gamma function, and you can actually do lots of crazy things with the gamma function, like show factorials of not integers, but that's besides the point. So 0 factorial equals 1. 1 factorial equals 1. 2 factorial equals 2. 3 factorial is 6. 4 factorial is 24. 5 factorial is 120. And so on. Get my dots up here because So as you can see, this denominator follows n factorial. So this can be rewritten, and I know 2 factorial is the same as 2, but just for completeness, I'm just going to write that out like that. This can be written as 3 factorial. This can be written as 4 factorial. And this can be written as 5 factorial. There. So these are all our different coefficients. So if we take this closed form of our p of x, let's rewrite it. I'm going to get rid of this factorial because we know what it is now. P of x equals this. But what does that really equal? Well, if you do term by term, we have a naught, then plus, well, what is a1? a1, well, a naught, what's a naught? Well, that's f of 0. So we'll just replace this, and we're just going from this. We're just taking this and replacing each a1, a0, 1, 2, 3, 4, 5 with what we found them to equal to down here. So a naught is that, and then we have a1x. But a1 is f prime of 0. And then we have a2x squared. So a2 is 1/2 factorial f double prime, oops, not capitals, got caps lock on, f double prime of 0. Then we have plus 1/3 factorial f triple prime of 0, x cubed. That's because this right here is equal to a3, and then you could just keep going. You could do all these. In fact, you could do it infinitely. Just get my dots again. There. So we can actually put this in a closed form and write this as we'll just follow the pattern. So n goes from 0 to infinity, and well, let's see. It's the 0th derivative is just the function itself. So it starts at the 0th derivative and goes first, second, third, fourth, fifth, and then at the same time it starts at 0 factorial, because you can write this as 1 over 0 factorial, and you can write this as 1 over 1 factorial. So if we use all these patterns, you know, x goes from x to the 0, x to the first, x squared, x cubed, we can put it all together into a pattern that fits this, and that is well, we already know the bottom goes by n factorial, and we know the top goes by f nth derivative evaluated at 0. And then it goes, well, we got the bottom, we got the f, and then after that it goes x to the n. And this is actually the Maclaurin series. We'll get to the general Taylor series in a second. But notice how it follows this. So if n equals 0, this is 0th derivative, which is just f, then 1 over 0 factorial, which is 1. I know it looks weird that has 0 in the denominator, but 0 factorial is 1. And then we have x to the 0, which is just 1. And then we move up n, and we get all these. Now, remember before I said that you can center it wherever you want. And basically that amounts to just shifting this polynomial so that when you evaluate it at that point, the polynomial equals 0. Well, all the terms with x equals 0 just as they did before, which would amount to just shifting it. So that's gonna be, if we do that, it's going to be, oops, we just have to shift it. It's just going to be x minus c, where c is the number we're shifting it to. There. So you see it, like when we plug in c here, all these terms go out. So we can that enables us to evaluate the function at any point. But I mean, you have to sort of put it in a special, you know, yeah, it enables you to do all any value you want of the function. So all we have to do is modify this formula to write it as f of c instead of f of 0, because we're evaluating it at c, not at 0. And that is basically it. One last thing. You can't forget what we just did. We replaced all the x with x minus c. There. And this right here is your Taylor series formula. You can, from this you can find any Taylor series of any function. And for example, I'll probably prove this in another video. E to the x is equal to, and runs from 0 to infinity, of 1 over n factorial, or x to the n over n factorial. This is equal to e to the x for all x. It converges for all the numbers. And amazing formulas come out of this. Believe it or not, e to the I theta, or e to the I pi equals -1, Euler's formula comes out of this. Or if you write it as e to the I pi plus 1 equals 0. The 5 most common math numbers all in one equation is Euler's formula. And just amazing. Yeah, amazing things come out of this formula right here. And this Taylor series have so much power, and they're just, you know, they're awesome. So, you know, this whole shifting business makes, you know, It might be a little tricky to understand at first, but just go through some problems. I'll make another video about doing examples, but that's basically it for the derivation. Not too bad. Really not that bad. Amazing though. Thanks for watching.